Okay, good afternoon, and now I will go and do the rest of this first part of chapter 23. Now, most of the time we use Faraday's and Lenz's law together. Sometimes we call it Lenz's rule. Okay, now this is really mainly, I would say, Faraday's law is going to be used to calculate the value or the magnitude of the EMF induced, and Lenz's law is going to indicate the direction of the current. Now, that EMF that is going to be induced depends on more than one factor. First, it is directly proportional to the change in the flux. This is not theta, this one, sorry, should be phi, delta phi. Now, how we can change the flux? The flux can be actually changed based on the current in the, we call that primary coil, or changing the area of the coil, or anything that is gonna make changes to the flux, like changing the area, changing the angle. All of these are really changing the flux. And also EMF has to do with the time, and it is inversely proportional to the time. Then as the time is getting shorter, we're gonna have more EMF. And of course, usually we don't use one turn, we use multiple turns, or like, a certain number of turns that they are going to also affect the, the EMF. EMF equal negative N times delta phi over delta T. This negative is coming from Lenz's law, because Lenz's law here, it said that the minus means that the EMF creates a current I and magnetic field that opposes the change in the flux delta phi. What does that mean? If the flux is increasing, then you are going to say that B original and B induced, they are going to be in opposite direction. Nature doesn't like things to increase without a boundary. Then if we will have the flux trying to actually to increase, there is something that is going to say stop, and is going to make it slow down. Okay, and there is we're going to see that usually we will talk about B original and be induced, and here I will say if we are going to have the flux increasing, then B original and B induced, they are going to be in opposite direction. If we are going to have the flux decreasing, then they will be in the same direction. Here showing you how we're gonna apply Lenz's law. Usually you're gonna have, this is a bar magnet, and that bar magnet, of course, you know that it has a north and south. And now when it is coming closer to this loop here, what's gonna happen is that the flux is gonna increase. Now remember the magnetic field here, be magnetic, and that was, I will say, this is my original. It is pointing to the right. Therefore, the magnetic field for the coil should be pointing to the left, because remember, there is an increase in the flux, then the two B's, they are going to be in opposite directions. And based on the direction of the magnetic field, you are going to use the right hand rule. Like this is the magnetic field pointing, like the fingers, they're gonna point in the direction, then I is gonna be going in this direction. Also, in the second one, we have like the magnet, we are bringing the magnet away from the coil, and therefore be magnetic drug, the original one and the one induced, they should be in the same direction, and based on that we are going to have the current going in the clockwise direction. Now this is when we reverse the I would say the magnet, like we have the south instead the north, is gonna be very similar to the B. Now first you're gonna ask increase or decrease in the flux. Okay, this is how we are going to understand how the current will be determined. Then if increase, induced will be opposite direction. Decrease means induced will be in the same direction. This is the problem solving strategy for Lenz's law. We use Lenz's law to determine the directions of the induced magnetic fields, currents, and EMFs. Make a sketch of the situation for use to visualize and record directions. Determine the direction of the magnetic field, which is, I will say, the original. Determine whether the flux is increasing or decreasing. Now determine the direction of the induced. We said if there is an increase in the flux, opposite to the original. If there is a decrease in the flux, they are going to be in the same. We are going to use the right hand rule to determine the direction of the induced current that is really responsible for the induced magnetic field. Okay, the direction or polarity of the induced EMF will now derive a current in this direction and can be represented as current emerging from the positive to the negative and returning to the negative terminal. Here, just one example showing you that you have two coils here. What is the value of the magnetic flux at coil 2 in figure 23.56 due to coil 1. Now one thing that you need to know here that I will say I will say here, you need here, you're gonna have two coils. One of them, it doesn't have a current at all, and the second one, it's gonna have the current. And based on that, I will say you're going to determine what is really the coil 1 magnetic field. And based on the right hand rule, you can use the right hand rule and say the magnetic field is gonna be out of the page, and it is making 90 with A. Now A, it is the magnetic field, it is out of the page here, and the A like from the screen towards me, and I will say the area is gonna be along the y-axis up, and therefore the angle between them is 90, and therefore phi will be a cosine 90, and cosine 90 is gonna be 0. Then the flux is gonna be 0. I want you always to remember that the flux, it is as if like the magnetic field that we are going to have here, it's gonna be lines going out of this, and none of these is gonna cut the coil 2, and therefore the flux is gonna be 0. Also, it's the same here for the second one. The wire is gonna have a magnetic field that you're gonna use the current. You're gonna use your right hand rule 1. Then the current is gonna go up, and then at the, I will say the coil, we are going to have also the magnetic field perpendicular with the area, and then also the flux is gonna be 0. Now this one here is I have a coil that is at different positions here, coil 1 and 2 and 3, and we are going to assume that the coils are lying in the plane of the circuit. and we are going to find when the switch is gonna close. Okay, what is going to be the directions of the currents in coil 1, 2, and 3? Now, after I close the switch, the current is going to go from positive to negative. Then I will say here for 1, I have the current going in this direction, and therefore the magnetic field of this current is going to be having the magnetic field is going to be into the page. Okay, and here, because we are closing the circuit, then I will say that phi is increasing, and therefore the original and the induced, they're gonna be in opposite direction, and therefore we are going to have like I would say the crosses represented the original, and then the induced is going to be out of the page, and using the second hand rule is going to make it counterclockwise. Of course, we can apply the same thing for the other two coils. Now, when the switch has been closed for a long time, there will be no change in the flux and then no current in all. Now, when the current is open, all will be opposite, because now there is a decrease in the magnetic field, and there will be a decrease in the flux, and therefore we are going to have the opposite. All right, now I will, of course, I prefer also to go over this question if you have any questions with it when we go back to the lecture. This is the last one here. I have 0.25 meter radius, 500 turn coil is rotated 1/4 of a revolution in 4.17 milliseconds. Originally having its plane perpendicular to a uniform magnetic field, and find the magnetic field strength needed to induce an average EMF of 10,000. Then the equation is, here we are interested only in the magnitude, and therefore I did not add the negative. EMF equals N delta phi over delta T, and delta phi, it is the magnetic field times delta A times the times the number of turns divided by T, and here the EMF that is induced, it is 10,000, and delta T, the time, it is 4.17 10 to minus 3 seconds. The number of turns is 500, and the area, it is pi times the radius, which is 0.25 squared, and then the magnetic field will be 0.425 Teslas. Thank you, and see you soon.